interest to the audience here, because it involves combining multiple types of data types, seismic reflection studies at the basin scale, GPS data, geomorphic signatures, to unravel the story behind the evolution of the crust structure beneath Northeast India. So, having said that, let me introduce Professor Mitra a little more. You must have read about him already in the emails, but Professor Mitra currently works at IISER Kolkata and was previously at IIT Kharagpur. It was there at KGP that I got the opportunity to be mentored by him for at least 2 years. My master's thesis was under his guidance. He has a PhD from Bullard Labs, University of Cambridge, which is pretty famous. He has multiple awards that testify to his quality of research. He has got the INSA Young Scientist Award, the National Geoscience Award by the Ministry of Mines, and he's also an elected fellow of the Royal Astronomical Society, among others. Having said that, with that, I want to pass on the mic to Professor Mitra. Thank you.
Okay, thank you very much, Amit, for the very kind introduction and for inviting me to give this talk. So can you all see my screen? So do you see the first slide?
Yes, we do.
Okay, so I'm going to talk about the crustal structure and deformation of the Eastern Himalayan plate boundary system. And this will basically be a story of how the northeastern part of the Himalayas work, but also away from the boundary of the Himalayas. I'm not going to talk a lot about the technique, but I'll kind of tell you the story. And then if you're interested, I can talk about the techniques which are quite standard in broadband seismology. So here is the outline of my talk. So I'll tell you the big picture question, then I'll introduce you to the Himalayan plate boundary system, tell you a bit more about the Eastern Himalayas and the objectives of this work, then talk about the crustal structure, the earthquake sources, and then combine all of these to understand how this region is deforming, what is supporting the Shillong Plateau, and so on and so forth. So to start with, this is the big picture question that we ask: how do plate boundary systems evolve? And what you see here is a map of earthquakes across the alpine Himalayan belt. So the red dots are all the earthquakes in the last 50 years, which are of magnitude greater than 5. So once you look at a map like this, what is remarkable is the difference in distribution of these earthquakes in the oceans and in the continents. So in the oceans, you can very clearly see that there is a thin line of all these earthquakes. So you can join all these dots and draw the plate boundary. So plate tectonics is what explains how these regions are deforming in the oceans. Whereas if you come to the continents, you can see that there is this broad zone of distributed deformation. So if I were going to join all these dots to actually draw a plate boundary, I'll actually go mad. So this won't work. So therefore, the language of looking at deformation in the continents is actually continental tectonics. And if you looked at the earthquakes that happen across this broad zone, let's say India and Eurasia, where you can see that India is kind of found getting into Eurasia, nothing happens to India. There are very few earthquakes. It's very rigid and strong, whereas it's smashing up everything starting from the Himalayas into the Tarim Basin and beyond. So the style of deformation also changes across these kind of regions. And that is what we are going to focus on today. My focus will be in the India-Eurasia collision. So let's take a closer look at this. So when you have these kind of continent-continent collision, where you have the Indian plate colliding with the Eurasian plate, the first thing that you would notice is that there is a formation of a fold thrust belt, an FTB, which is a zone of intense deformation. And here again on the map on your left are all the earthquakes plotted, color-coded and plotted by these circles. So the shallow ones within 40 kilometers depth is white, 40 to 80 is yellow, and then 80 and deeper is orange. And you can see that there are all these earthquakes all across this region. So this is a zone of intense deformation. When this happens, there is underthrusting of one plate beneath the other. In this case, the Indian plate is underthrusting. And if you look at the cartoon on the right, you can see the Indian plate actually going down underneath the Himalayas and southern Tibet. And this leads to the flexure of the Indian plate. And therefore, what it forms is what is known as a fold-land basin. So if you looked at the region just south of the fold thrust belt, in the central Himalayas, this fold-land basin is about 200 kilometers wide. The width of this basin obviously is guided by the elastic thickness of the plate that you are flexing. So here, obviously, India has a strong lithosphere. It has a thick elastic plate, and therefore you have a very wide fold-land basin. Now, if you look at the ongoing collision in the present day, which is measured by GPS geodesy between a point, let's say in Bangalore, and one in Siberia, you can see that the ongoing collision takes up about 30 to 40 millimeters per year of shortening across this region, of which almost half is being accommodated within the narrow belt of the Himalayas. And this is stored as elastic strain within the locked zone. And the locked zone is the shallow part of the boundary which separates the downgoing Indian plate and the overriding Himalayas, which is marked on the plot on your right. And that is the region which produces all the big earthquakes. So if you looked at a map of earthquakes in the Himalayas that has happened in the last 600 years, so what you see here are all the mega thrust earthquakes, which are greater than 7.5 magnitude. And these are the rupture areas of these approximately are drawn as the ovals that you see, and the numbers within them are basically the year of their occurrence. And you can see that the entire Himalayan plate boundary is actually rupturing in big earthquakes. So
sorry,
this is
sorry
yes.
to interrupt. Sorry to interrupt.
Yes, go ahead.
I can't see your cursor. Oh, now, yeah, okay.
You can't see my cursor. Okay,
Yeah, is it possible to? Yeah, that's better, much better.
Yes,
yeah.
yes, yeah.
Great, thank
Does
you.
that work?
Yes,
okay.
yes.
So here you can see all the earthquakes that are actually that has happened in the Himalayas. These are all mega thrust earthquakes, which essentially is happening in that elastic strain zone. So now if you look at the region immediately south of the Himalayas, which is this box region here, you see that the Indian plate is actually not undergoing very much of deformation, as I said. So there's very little deformation that's happening south of the Himalayas. But this simplicity does not hold good for the entire range of the Himalayas. So if you come to the northeastern part of the Himalayas, which is in this red box, it forms a third of the Himalayan arc and actually controls how strain is partitioned not only within the boundary, but also away from the boundary. And you can see that the earthquakes are not confined up to the Himalayas, but they pour out across this region. So obviously, this region is different than the central part of the Himalayas, and that is what is going to be the focus of my talk today. So this is what I call as the Eastern Himalayan and the Indo-Burman plate boundary system. So here there are several tectonic elements. You have the Sikkim Himalaya and the Eastern Himalaya, which are marked up here. You have the Brahmaputra Valley, which is basically the foreland basin. Then you have these Shillong Plateau and the Mekir Hills, which are basically uplifted basements within the foreland basin, which is not present elsewhere in the foreland. And then to the south of it, you have the Bengal Basin, which is a very thick pile of sediments. And to the east of it is the Indo-Burman convergence zone, where the Indian plate actually is subducting underneath the Burma microplate. So here are a few other tectonic elements, which I'll also be referring to. So you have the Dauki fault, which basically bounds the Shillong Plateau to the south and separates it from the Bengal Basin. There is an Oldham fault, which is a buried fault and was actually detected by modeling geodetic data, which is to the north of the Shillong Plateau. You have a Kopuli fault zone, which is a set of strike slip faults which separates the Shillong Plateau from the Mekir Hills. And then you have this Eocene Hind zone, which is a gravity high and is kind of understood to be the paleo boundary of the continent. So these are the ones which I'll be referring through my talk. So to put you in perspective of all of these, so here are all the stuff that I'm going to talk about. Now, what is this zone like? This is, as I said, a zone of interaction between India under thrusting beneath the Himalayas to the north. And the figure that you see on the left is an old work that we did where we first showed that India actually goes underneath the Himalayas and southern Tibet as a continuous crustal layer. And you have the thinnest crust underneath the Shillong Plateau. And if you look at these earthquakes, which are to the east of it, if I took a cross section across this blue line, you can clearly see that the earthquakes actually dip. And although these are earthquakes out of the catalogs, the depths are not very well constrained, but still you can see that the Indian plate is subducting underneath the microplate, which is the Burmese microplate, and it's also rolling back. So this is a very complex zone of interaction, and that is the reason why you have all these earthquakes which are away from the plate boundary. So this region is actively deforming. Now, there are significant deviations, as I said, from the central part of the Himalayas. And let me point out these deviations. The first one, as I said, is that there are earthquakes away from the plate boundary. So there are what we call as intraplate earthquakes. And there is a whole zone of distributed deformation. It's not just the earthquakes. If you look at the GPS geodetic data across the southern boundary of the Shillong Plateau, there is convergence which varies from 3 to 7 millimeters per year, going from west to east. And this has been used by Roger Billam to actually argue that there are all these micro or microplates which are basically rotating in a clockwise manner. But obviously, this is a wider zone of deformation. if you looked at the width of the foreland basin just south of the eastern Himalayas is much narrower than what we saw in the central Himalayas. So this is about 50 kilometers as opposed to 200 kilometers. So there's something else that's happening in this region. Now, if you look at the sediment thickness in the foreland basin, here is a plot at the bottom where you go from the western Himalayas to the eastern Himalayas. This I've taken from one et al. And you have a color scale which tells you the thickness of the sediments. You can clearly see that the sediment is as thick, or the foreland basin is as deep as about 7 kilometers south of central Nepal. But as you come to this region here, the sediment thickness is less than a kilometer, which most probably tells you that it's not just the Shillong Plateau which is being uplifted. Most probably it's the Brahmaputra Valley which is also getting uplifted, and the sediments either there is less accommodation space or has been removed through time. And then finally, if you look at the positive elevation of this plateau, you would expect that this positive elevation would be supported by some crustal route through isostatic balancing. But if you look at the Booker gravity anomaly, this is a very old map, and I'll show you recent maps of free air anomaly in a bit, but this is good to demonstrate what I'm trying to say. So this positive elevation is associated with a positive Booker gravity anomaly, which essentially means that there is no crustal route which is supporting the topography. And therefore, we need to know what exactly is supporting the Shillong Plateau. So these are distinctive differences of Northeast India from the rest of the Himalayan plate boundary system. And we need to understand these deviations so as to understand continental tectonics, which brings me to my objectives, 3 broad objectives that I'm going to talk about today. One is to understand what the crustal structure is, and also understand what the lateral variation in the structure is. Or in other words, what is the disposition of the moe? Are there offsets in it? Is it flexed? How does it vary across the Shillong Plateau and the Bikar Hills and the region across here? So what is the sediment thickness? What is the nature of the Bengal Basin crust? So these were questions which we didn't have answers. We only saw that there are variation in the topography. We saw that there were earthquakes. So these are questions that I'll address. Then what I'll do is, once we know the structure, then we look at the earthquake source mechanisms to understand how they are related to the structure. Or in other words, what is the role of the bounding structure in controlling the deformation that you see? And then finally, yes, please go ahead.
Sorry, can I ask questions while you are going?
Yes,
or,
yes, absolutely, absolutely. Go ahead, no problem.
So you talked about the structure as well as the sediment thickness and all that, those aspects you'll be, but maybe this is not important, but I want to ask you, is there a compositional difference also as you go from west to east?
Yes, yes, I'll show you all of these. Yes,
Okay.
there is. Yeah, yeah, absolutely. Okay. Yeah, and the third objective is to look at the support for the uplifted Shillong Plateau, as I said, or in other words, to understand what the elastic thickness and its relationship to the seismogenic thickness is. And while I do this, I'm also going to combine my results with GPS velocity field, look at Bengal Basin tectonics from a few seismic lines that has been shot across Bangladesh and the sedimentology work, and combine it with low temperature geochronology to see what it tells us about the timing of the uplift and how I can combine that with the structure that I see. So this is what I'm going to do now. So to start with the structure, we had actually set out a broadband seismological experiment in this region. We started long back, about 20 years back, and you need to understand this is not a region which was really accessible at that point of time. So nowadays, when we put out a network, we actually put stations in a grid fashion. Whereas here we were severely restricted by where we had access. And therefore, the triangles that you see, they have gone in phase-wise manner, but only in places which we could access. And then we tried to abstract as much information as we could from this region. There were different networks which ran stations. We ran some which are the ones in red. There are these stations in Banglapire, which is in Bangladesh, which are in yellow. IMD gave us a bit of the data, and then we had some stations from the Northeast Institute of Science and Technology. So these are all the stations from which we use data to understand the structure and also study the earthquakes. For looking at the structure, I use teleseismic earthquakes in a distance range of 30 to 90 degrees. And these are plotted on the map here. So the stars are the earthquakes that we have used to look at the structure. What we use is basically called receiver function analysis. So I'll spend a couple of slides telling you a bit about this. So if you see the top plot, this is basically a generic form of, let's say, a teleseismic earthquake recorded on the vertical component. You have body waves, you have surface waves. Receiver functions are basically body waves and its conversions in the structure. So these are sensitive to impedance contrast boundaries underneath the station. So let me demonstrate this a bit more with a cartoon. So what you see in one, if you have an earthquake marked as E, if it is recorded at a teleseismic distance in a receiver R, and the region just underneath the receiver, if you approximate that as a stack of layers, what you can do is you have a plain P wave which hits this boundary and then transmits through these layers, converts and reverberates, and you can use these to actually look at the structure. So what you see in 2 is basically the plain P wave which transmits. And if I show you a cartoon of what these receiver function looks like, this is what it would look like. So the red lines on the plot in 2 are basically the P wave which is transmitted and reverberating. The blue ones are the S waves which are converting from either the transmission or the reflection from the free surface or any discontinuity within within the earth. So let's say like the MOHO or mid-crustal discontinuity, and you have all these phases. The way you isolate this signal is by deconvolving the vertical from the radial and the tangential. On the radial, you'll be left with all these final S legs, and that is what you're seeing in 1 here. So you have the PP, which is the direct arrival of the P wave. Then you have the P to S conversion, which is PS. Then you have reverberations, which are like P, P, PS, and so on and so forth. So what you would have is the amplitudes of these arrivals will actually be controlled by the impedance contrast at this boundary. And the offset time of each of these will essentially tell you the thickness of the layer, given that you have some control of the velocity. And what I'm going to do is I'm going to use this to look at the geometry of the MOHO and the variation in crustal thickness. So here is a real example of receiver functions plotted as a function of ray parameter, which is basically the inclination of the ray. We want these rays to come in as steeply as possible so that it looks at the structure underneath the stations, but obviously they are inclined to the vertical. And what I show in 2 is basically how they are inclined, and therefore they would actually pierce on any discontinuity. Let's take the MOHO at different points. And what we can do is we can actually look at the piercing points of these rays which come into the station, surrounding the station, and that is plotted on the plot on your right. So these are color coded by the stations. So you can see all these piercing points which are surrounding the stations. So these are the ones that we'll use to actually look at the lateral variation in the structure. So let me start by looking at a few points. So again, this map here, I'll zoom into this map, which is in 3, and I look at the northern edge of the Shillong Plateau and the southern edge of the Shillong Plateau to see how the structure varies. So here again, in 1 is the map. So there are 2 boxes that I've drawn here. This B and C is what I'm going to talk about. This box B is across the central Shillong Plateau, the northern edge of the central Shillong Plateau. And what you see are 3 stations, Baihata, Guwahati, and Nongpo. And you see in pluses are basically the piercing points for each of these stations. What I do is I look at the receiver functions and I plot them as a function of distance by stacking them in small bins. And what you can clearly see is the PS arrival, which is the P to S conversion. Now, what you see on the left here is some guideline that we use to understand what the variation in the thicknesses are. So imagine that you have a VP of 6.5 kilometers per second and a VPVS of 1.73. It's a Poisson solid. If that's what you assume, a 1 second delay would translate to about 8 kilometers in thickness. So here what you see is a 4-second delay in the PS arrival from the PP. And then once you go across to the Bengal Basin, I'm sorry, the Brahmaputra Valley, which is the foreland basin, you see it's about 5 seconds. So over this distance range, you would need a real flexion on the MOHO, which would be about 30 degrees. So the same thing can be done across the eastern region, across the Mikir Hills, where you have this station Borjuri, and you have Tejpur, and you look at these, the change, it's similar. So you have a real flexure or an offset on the MOHO across the northern edge of the Shillong Plateau. So we think it's a flexure because we have done a lot of synthetic tests. We calculated receiver functions for different dips on the MOHO, and what fits our data is a flexure, which is quite strong. It's about 30-degree dip on the MOHO. Now moving to the southern edge of the Shillong Plateau, which is this box B here, and I've blown this up here. We are looking at a station Cherrapunji where you have rays which are coming in from the north and ones which are coming in from the south. And here you can see that there is a remarkable difference, and that is like 5 seconds to the north and 6.5 seconds to the south, which essentially tells you that over this short distance, there is at least a 12-kilometer offset. And we think this is an offset, and I'll show you once we do the formal inversions, this will show up as an offset in the MOHO across this boundary, and we have all the stations to show this. So what I'm telling you is that there is a MOHO flexure to the north of the Shillong Plateau, an offset to the south from the Shillong Plateau in the Bengal Basin. Now, let me show you more about the inversion that we do. So as I said, receiver functions are good to model the depth of the discontinuities, provided that you have some control on the velocity. So here, what I'm going to do is I'm now going to introduce surface waves into the system. And this is the bracket of surface waves, let's say, on that generic form of the seismogram. What you can do is you can actually abstract information about the group and phase velocity. Surface waves are dispersive, so different frequencies travel with different velocities. So if you take out the group velocity as a function of period, you can run a tomography, and then what you can do is for the point surrounding your station, you can actually get a group velocity dispersion curve or a phase velocity dispersion curve, and that is sensitive to the vertical averages of shear wave velocity. So if I jointly invert the receiver functions along with the group velocity curves, I would have a control on both the velocity and the discontinuity. So what it gives me is a shear wave velocity structure. And that is what I'm going to show you. This is one example. So what you see at the bottom is the receiver function. So the gray dashed line is the observed bounds. The red and the blue lines are the synthetics calculated for the model on the right. And the dispersion curve, so here you have period, you have group velocity. Again, the blue and the red are basically dispersion curves, synthetic dispersion curves calculated for the model on the right. And the black bounds are basically the observation of the dispersion data that we have. So what we are doing is we start with a thinly parameterized model, which is the blue model, and then we thickly parameterize it to actually highlight the major features in the structure. So here you can see the three things that I'll be interested in is the Moho depth, which you can see marked here, the average VS in the crust, and if there is layering within the crust. And these are the phases which are being constrained by the receiver function and the dispersion data. So this is one example from one station. Now I'll walk you through all the different examples that we have. So let me start by looking at the northern part of this region, which is in the Brahmaputra Valley. So what you see in one are three models from the stations in the Brahmaputra Valley. Things that we need to notice here is that the crust is about 40 plus minus 2 kilometers thick, and the average shear wave velocity is 3.5 kilometers per second. And the VPVS ratio, which I have not plotted here, is about 1.73. So it's like a fail-sick crust. If you look at the western edge of the Shillong Plateau to the north, you would see that the VS is again similar. The crustal thickness is slightly less. It's about 36 plus minus 2. If you went into the central Shillong Plateau, which is this plot here, 3, again, you have the same kind of crustal average velocities, but the crust is much thinner. It's about 31 plus minus 2. If you look at the station Bordjuri, so that's in the Mikir Hills, similar in structure as the Shillong Plateau. So here, what is important is you have the same average crustal velocities. You have similar VPVS ratio, which tells you that the composition is more or less the same. However, there is some lateral variation in the thickness of the crust, with the thinnest crust beneath the Shillong Plateau and the Mikir Hills. Now let me move to the south of the Shillong Plateau. Here what I've done is I've rotated the map in a clockwise manner. So north is pointing in that direction. Here is the edge of the Shillong Plateau, and I'm showing you three different sets of models. One from the southern edge of the Shillong Plateau, one at the northern edge of the Bengal Basin, and one within the Bengal Basin further to the south. So here you can see that it's the similar kind of VS that you have, average VS 3.5. It's the same kind of crust that we have seen in the central Shillong Plateau, slightly thicker, 35 kilometers. What is remarkably different is this region immediately off the edge of the Shillong Plateau. You can see that this crust is down faulted, and you see sedimentary layers which are really slow, about 3 kilometers per second sedimentary layer. They're a thick packet of sediments, and because these rays are piercing through the sediments and are being recorded on the Shillong Plateau, so you again see a glimpse of the Shillong Plateau crust on top. And then as you go out into the Bengal Basin, this is a much thinner crust with a higher velocity, a higher VPVS ratio, stacked with about 18 to 20 kilometers thick sediment on top. So there is a clear transition as you go from the Shillong Plateau into the Bengal Basin. Remember this as we move forward. So now if I, yes, please go ahead.
If you go back to the last slide.
Yes, please.
So in the middle, or the area, the Moho is not that conspicuous in terms of the velocity change.
Yes, it is here, but it's not so much here. Yes, you're right. But
so is there a reason for that?
One of the reasons for this is that a part of the signal is actually being overridden by the reverberations from the sediments, which are very strong, because you see the impedance contrast across this boundary is very strong, and this kind of reverberates somewhere around the Moho. But here you can see this to be quite sharp. Yes, you're right. So here it's not. So what we do is we generally use a change or a gradient to pinpoint the Moho. So here it's like 48 plus minus 2 kilometers. That's what we think is the Moho. Yeah.
And my guess is that you do not have enough sampling to sort of constrain the size of that area. I mean, whether it is pretty localized or is it a little bit more
No, we
pervasive?
do. Yes, yes, that's a very good point. We do actually. What I'm showing you is only a subset of the models. So we had a station here in Jaflong, which has a large number of receiver functions, and then one slightly to the south of it, which I didn't put in because of time. But we could see the transition. And what is very, very significant is we can pick up the transition where this is down faulted, and then it goes into the transitional material. So we can see that. But yeah, obviously we see it at points of receiver functions and then make it into a 2D by looking at the piercing points. But yes, we can see the transition across that boundary. So what I think is happening, which I'll tell you in a bit, is that the Shillong Plateau crust is down faulted and then it thins out as you go further to the south. Okay, yeah, but I'll show you some more examples. But we have more stations from which we have seen this transition. Yes.
Okay, thank you.
Okay, yeah. So now let me summarize what I've just told you. So there are two things that I'm showing you. One, on the left is the sedimentary thickness, layer thicknesses, and the right is the basement thickness, which is essentially the crust without the sediments. So things to note here, look at the Brahmaputra Valley. As I said, that there is very thin veneer of sediments, nowhere more than 1.5 kilometers. Over the Shillong Plateau, it's almost devoid of any sediments. But as you go to the south, across the edge of the Shillong Plateau, which is the Dauki Fault, you immediately see that there is this very thick packet of sediments, which thickens as you go out towards the Bay of Bengal. And here is the Eocene Hind zone, which, as I said, is this gravity high, and we think that that's where the continent ocean boundary was before the Himalayas started growing and the sediments poured in. Here you can clearly see that there is a thickness change in the sediments, and you can see that it's like a packet of sediments which thickens as you go across the Eocene Hind zone. If you look at the basement thicknesses and the average velocities, so what you see north of the Dauki Fault, across the Shillong Plateau, Brahmaputra Valley, all of this region has an average VS of 3.5 kilometers per second, average VPVS of a felsic crust, and you have crustal thickness variations, the thinnest being underneath the Shillong Plateau. The moment you go across the Dauki Fault and to the south, you start seeing very, you see thinner transitional crust is what I call it. So you have average velocities which are larger, which are about 4 kilometers per second, and the crust thins. So it's about 20 kilometers in the central Bengal basin, and then thins as you go to the south. And you can see that change also across the Eocene Hind zone. So these are basically the summary of the structure that we have seen. Now, if I put that in a slightly different perspective, this is what I'm trying to tell you. So continental crust north of the Dauki Fault, and transitional crust with a thick pile of sediments on top south of the Dauki Fault. The Dauki Fault basically marks this change, where most probably the crust is down faulted by 12 to 13 kilometers. To the north, the Moho is flexed down. So basically the Indian plate, under thrusting the Himalayas, flexes it down because of the Himalayan load. And that's why you see the flexure where you have a change of 9 to 10 kilometer thickness as you go from the central Shillong Plateau into the Brahmaputra Valley. So this is a summary of the structure. Now, are there any other evidences which actually tells you that this is how it is? So yes, there is. So I go back to this work by Alam et al., where they looked at the tectonics of the Bengal Basin. What I'm showing you are two profiles from their paper. One is sort of east-west, and two is north-south. So what they saw is that across the Eocene Hind zone, the crust thins, and then what they call as the attenuated continental crust is what I'm calling as the transitional material. Transitional simply because it's transitional in thickness. So it goes from being 35 kilometers north of the Dauki Fault to 20 kilometers and then thins out into the Bay of Bengal. And if you look at the north-south profile, you can see that the Dauki Fault is a major structure which actually causes this change. So we'll come back to this. So before we again come back to this and try and make sense of what the Dauki Fault is doing, we need to look at the earthquakes, or in other words, we need to understand what these structures, the role that these structures play in controlling the deformation that you see across this region. For this, I will turn to the earthquakes. So this is a work that was done by my undergraduate student, Ajay Kumar. So we looked at about 42 large earthquakes, I mean, moderate size earthquakes, and also combined earthquakes from the previous studies which had good mechanism. So we used two different techniques. to look at these earthquake mechanisms, we do teleseismic waveform modeling for the bigger ones, which are bigger than 5.5, and we use local waveform inversion for the slightly smaller ones greater than 4 magnitude. So one slide on the methodology. So what we do is we relocate these earthquakes using phase travel time data. And then once we have the relocated earthquakes, we use waveform fitting to actually model these earthquake sources. So if you have a recorded waveform, which is from an earthquake source, so you convolve that with the structure that produces the recorded waveform if it's instrument corrected. What we do is basically we assume either a double coupled source. In this case, we are assuming a double coupled source. We can also do a moment tensor inversion. We convolve that source with the earth structure and compute a waveform. And then we kind of keep on updating our assumed double coupled source model till we get a minimum misfit between the recorded and the computed waveform. At that point, the double coupled source that we have is the mechanism for the earthquake. So this is a plot of all these earthquakes that we have looked at across this region. So they're again color-coded. Red ones are using teleseismic waveforms. Green ones are using the local waveforms, and the black ones are from the previous studies, some of which we had done in the past. Just to tell you what these symbols mean. So if you have a strike slip earthquake, you will have these 4 polarities, which will look like this. A normal fault obviously will be colored white in the middle, which is basically dilatation, and then dark on the sides, which means compression. A reverse one will have a dark one in the middle, which is basically compression in the middle. And then you can have combinations of the strike slip and the normal or reverse fault, which will produce an oblique motion. So that is what you are seeing.
So what magnitudes are these? What magnitude?
These are basically the ones which are red are greater than 5.5. The ones which are green are 4 to 5. We have nothing smaller than these. The other ones which have been taken from the literature are all greater than 5 magnitude. So these are mostly moderate earthquakes, nothing greater than 6.5 in this region.
So you can assume 0.4 force here, then point double couple.
Yes, we can. Yeah. So
Okay.
for all the teleseismic modeling, we can assume them to be a point source. Yes. Yeah. Okay. So now let me first point out the numbers which are above the beach balls. Ignore the numbers within the beach balls. These were basically codes for the numbering of the earthquakes. The ones which are in bold above the earthquakes are basically their centroid depth. And the uncertainties on these are kind of plus minus 3 kilometers. In better ones, it's like plus minus 2 kilometers. So look at these numbers, and you can clearly see that the entire crust underneath this region is seismogenic. There are a large number of earthquakes in the mid to lower crust across this region, which is important. Okay, so the entire crust underneath this region is seismogenic. Now let me point out to different regions. First, I start with looking at the region which is north of the Shillong Plateau, where you have these thrust fault earthquakes underneath the Bengal the Brahmaputra Valley. So this is because of the flexure of the Indian plate as it goes underneath the Himalayas. Now, the next set are these Kopili fault earthquakes, which are all strike slip earthquakes. And it has been mapped that the Kopili fault is a dextral strike slip fault, which most probably is like a bookshelf of faults. You have all these series of faults, which produces all these earthquakes. That's how I say that this is a dextral strike slip earthquake. This also continues underneath the Himalayas. The Indian plate is actually breaking in strike slip faulting in this region. So you see earthquakes like those ones there, and also continues down underneath the Indo-Burman ranges. So we have done back projection to look at the propagation of the energy, and we know that it's actually the fault plane, which is northwest, southeast, which causes all these earthquakes. So it's dextral strike slip faulting in the mid to lower crust in the Kopili fault zone. And then we look at the region in the Bengal basin. What is important here to note is that there are no moderate size earthquakes underneath the Shillong Plateau. We didn't see any in the last 20-25 years. Obviously, there are microseismicity which we couldn't track, but what we are looking at are the moderate size events. So these ones which are plotted at the southern edge of the plateau are actually at these points. So we just moved them around. So there are earthquakes in the Bengal basin, but they are all in the transitional crust. Look at the numbers on top of them. So they're all between 20 and 40 kilometers. So what we think is going on here is as follows. So remember that there is this Eocene Paleo passive continental margin, and you see all these strike slip earthquakes in the transitional crust. What we think, if you take a cross section across this region, imagine a situation before the Himalayas were built. This is how this passive continental margin looked like. So you have these transition going from continental material into oceanic material. So what these structures are most probably paleo rifts, which are parallel to the Eocene zone, and this kind of goes around the Dauki Fault. We think that the Dauki Fault is the bounding fault on the continent, and what we think is that these are all getting reactivated. The reason why they are getting reactivated as strike slip faults is because the direction of compression across this region now is almost subparallel to these faults. So if I put this in a little cartoon, this is what we think is going on. So here, the dextral strike slip faults in the Kopili fault zone are actually accommodating the convergence by through a anti-clockwise rotation. The ones in the Bengal Basin are sinistral strike slip faults, which are accommodating the convergence by rotating in the other direction. However, these are all moderate size earthquakes, and they do not account for the complete convergence across this region. Or in other words, the question is, what is the thrust doing? And we know that the thrust fault, which is the Dauki fault, is capable of producing 8+ magnitude earthquakes, 1897 being one of them. There is obviously a debate as to if it was on the Dauki fault or the Oldham fault. Doesn't matter. These are crustal scale faults, which produces big earthquakes, and these earthquakes are thrust earthquakes. So now let's look at what this is doing.
Can I
Yes,
question
please
you?
go ahead.
So looking at the strike slip motions that you are putting across the thrust, is it a pure thrust, or does this thrust also have some kind of a shear along it?
It most probably has a shear along it, but what I've put here are not the earthquakes on the thrust fault. No. So these are earthquakes which are either in north of the Shillong Plateau in the Kopili fault zone or south of the Dauki fault underneath the transitional crust. So on the thrust fault, there are no moderate size earthquakes in the last 20 years, whatever we have tracked. So nothing in the literature, nothing that happened on the Dauki fault. And therefore, we think that it's completely locked, and I'll tell you why we think so.
And is that the reason then the bulge is to the north of it, right?
Yes.
The flexural high you are showing is north of that. Because I was just thinking that if there is any kind of a strike slip motion or some component of it along that thrust, which is not a pure thrust, let's say, then in that case you might be compensating that high, but you are not. So that's why I was asking. So thanks for answering.
Yes, I think you're absolutely correct. I think there is a strike slip component on the thrust fault, but the problem is it has not produced earthquakes. Yeah. So, and also because the Indian plate is under thrusting or subducting underneath the Indo-Burman ranges, so there is obviously a component of pull in this direction, which will obviously make the thrust more oblique.
Yeah.
So yes, you're right. But the only way that we can track the thrust is actually looking at the long-term convergence and looking at the offset that we see from the structure. And that is what I'm going to do. So now, before I do that, let me quickly summarize what I've told you. So I've put these numbers 1, 2, 3, 4, and 5. So number 1 is you have continental crust underneath the Shillong Plateau and the Brahmaputra Valley. You have a flexure north of the Shillong Plateau, and that flexure is obviously because of the flexure of the Indian plate. Number 3 is you have a down faulted crust across the southern edge of the Shillong Plateau, and it's quite a large step. Number 4, you have this transitional crust with a thick pile of sediments on top. And number 5, the seismogenic thickness of the transitional crust is about 20 kilometers. So all the earthquakes are within the transitional crust from depth of about 20 to 40 kilometers. So now with this, let us take a closer look at this region across the Dauki fault. So what I'm going to do is I'm going to use the data from Yani Najman's work, where she actually looked at the reflectors in the Surma Basin and tried to work out the loading of the Bengal Basin crust because of the growth of the Shillong Plateau. So what she saw was that there were these reflectors which were actually dipping towards the Bay of Bengal till a certain point of time, and then they became horizontal, and then they started dipping towards the north. And that was used to say that that was the time the Shillong Plateau rock uplift started, and therefore the Shillong Plateau started to load the transitional crust in the Bengal Basin. And the timing of that is between 2 and 3.5 million years. If I turn that into a number of vertical uplift rate by using the offset of 12 to 13 kilometers on the Moho, because that is something which we believe is preserved. The topography is not, because it's eroding. And therefore that will give me a vertical uplift rate which varies between 3.5 to 6.5 millimeters per year. Now from geodetic data, we know that the dip of the Dauki fault would be somewhere around 45 degrees, take or give about 5. And if you turn that number into a horizontal convergence, it will be almost the same on a 45-degree dipping plane. And that matches with the GPS derived horizontal convergence in the present day, which is about 3 to 7 millimeters per year. So that tells us that the majority of the convergence is actually being absorbed by the Dauki fault. And this is a crustal scale fault. It's completely locked in the present day, most probably produces microseismicity. And that is something we do intend to do. We want to put out a network to look at the microseismicity and see what's happening, but it's not producing moderate size earthquakes. And we know that it breaks in big earthquakes like the Shillong earthquake of 1897. So this is one important thing that needs to be incorporated in hazard estimation in this region, right? So now,
so have you? Sorry,
Yes,
I mean,
please.
I mean, you are showing
Yes,
so
please,
many interesting features, and I mean, a lot of nice work actually. So if you look at the Shillong plateau height,
yes,
and then if you are saying that Dauki fault, that is what is accommodating most of this. I mean, that diagram
yes,
is pretty telling, because if that was not the case, then you won't
yes,
see the Shillong plateau high and the highest point towards the Dauki fault. It would be in the other way. So there are some observational correlations too to
yes,
support your hypothesis. I mean, to support your theory.
yes,
So that,
yeah, yes, absolutely.
that's
Thank
just
you
an
so much.
observation, not a question. I just saw that, and I was going to answer.
Yes, yes. And that is what I was going to show you next. So obviously, the next question that we will ask is what supports the Shillong Plateau load. But before we do that, sorry, I missed the slide most probably. Oops. Oh, sorry. Yeah. So this is something which I missed. Sorry. So obviously the Dauki fault, as you say, is a fault which stands out. So you can clearly see if you were on the Shillong Plateau looking down at the Bangladesh plains, this really stands out as a big topographic high. And the Dauki fault sits at the base of it. So that is what is actually absorbing all this motion. Sorry, I missed this slide somehow. I don't know how. But anyway, yeah. So going back, so the last question that I'm going to ask is what supports the Shillong Plateau load? And for that, what we do is we do flexural modeling using gravity data. So what I'm showing you on the left is the free air gravity map. So the free air anomaly is red when it's positive and blue when it's negative. So what you can clearly see on the Shillong Plateau that the free air is positive, and south of it, you have this negative. So if the Shillong Plateau is without a crustal root, obviously you'll have positive free air gravity, which tracks the topography. And if you have flexure in the basin, you would have negative gravity anomaly because you have sediments on top, which reduces the density. So what we did is we are actually going to model the gravity away from the load. And if you are looking at the wavelength of the flexure away from the load, you solve the fourth order differential equation where your flexural wavelength is guided by the elastic thickness only. And that is what we do here. So what you see on the top right is the dashed line is the bound of the free air gravity stacked in this box, which is shown in green. And what you see as blue is the modeled gravity, free air gravity for a varying elastic thickness of this layer. So we vary the elastic thickness from 0 to 80 kilometers. So that is the TE. And we try and match the observed gravity with the calculated gravity. And we can see a very clear minima, which lies between 5 and 20 kilometers. So 20 kilometers is the upper bound of it. And that tells us what the elastic thickness of the layer is. And we think that is what is supporting the load of the Shillong Plateau. Just to remind you, the seismogenic thickness is also 20 kilometers. So the seismogenic thickness gives you an upper bound to the elastic thickness, and they match. So the layer which is actually causing earthquakes, which is deforming on a shorter time scale through earthquakes in a brittle manner, is also the layer which is supporting the load of the Shillong Plateau over a geologic time scale. And therefore, it doesn't have a root, so it's being dynamically supported by the flexure and the faulting on the Dauki fault. So this is where I'm going to stop. So here is a summary. Just to quickly remind you, we see crustal thickness variations with the thinnest crust underneath the Shillong Plateau, felsic continental crust north of the Dauki fault. South of it is the transitional mafic crust. You have the Eocene hinge zone, which marks the paleocontinent margin. And that is the region which kind of shows you the transition, the Dauki fault being the northernmost of these faults. So this is the basin margin fault, which has an offset on the Moho. The long-term vertical uplift rate and the horizontal convergence rate from the GPS data in the present day match, which basically tells you that the Daoudi fault is absorbing majority of the convergence that you see across this region away from the plate boundary. The entire crust beneath Northeast India is seismogenic, which tells us it's cold, it's brittle, it can actually support the load of the Shillong Plateau. So before I end, I should acknowledge my co-authors, Ajay Kumar, Kajol Bora, Keith Priestley, and Vinod Kaur, and my students and colleagues in the ISR Kolkata Computational Seismology Lab. And here at the bottom is a picture of what my institute looks like. So it's a new institute. We are only 18 years old. The new campus came up less than 10 years back. And if you all are visiting India, do visit us, write to me, and we'll be very happy to host you. Thank you very much.
Thank you, Professor Mitra. That was a very nice and very welcoming and refreshing talk. Really appreciate, and would like to see more of that. I'll thank Amit also for making that. Samarjit, you have raised your hand. Any questions?
Yeah, I would like to echo that. It's an excellent talk. Reminds me of the campus days, gravity, seismic. My question is about the slide before your summary slide, Shupio. So how do you select that upper bound? Because the misfit plateaus out. Are there any other conditions or constraints that helps you to?
Yeah, so you can see a clear minima, right? So in the black curve, you can see a clear minima.
Right. My question is around that upper bound, which is the 20 kilometer.
Yeah, but so it's kind of lower than that. That is what I meant. Yes.
Okay.
So that kind of puts an upper bound on the TE. So it's the TE is most probably lower than 20 kilometers. And also you see from the TS, that's about 20 kilometers. So yes, definitely it's lower than 20.
Right. Okay. Thank you.
Yeah.
Hey, can I ask a quick question?
Yes, please.
So now, are you not recording any local earthquakes in your network?
When we ran the network, it was so sparse because the network that I showed actually did not run at the same time. So it kind of was staggered. So we started with 5 instruments, then a few more, then a few more. And this was an old experiment, and then we started adding instruments to it. So we have not we have recorded local earthquakes, and we use the local waveform modeling for the ones which are greater than 4. The ones which are smaller, we can't do anything with the ones which are not in the catalogs, because we can't build a catalog. We don't have a network to build a catalog. So unless it's in the catalog, we can't do much. So that's what we are limited by.
Now, the reason I was pointing this out is that I thought that maybe you can get a higher resolution structure from local events. But one other question before I let others.
Yes, please.
So one is that this Shillong Plateau has been modeled as like a pop-up tectonics or something like that.
Yes.
So it seems like your model is sort of along the same line, looking at the structure that you have, right?
Yes. Yes, it is a pop-up. Yep.
Okay. Now, there was a recent publication I saw where they did some local earthquake or something. I don't know what kind of data they use, but it's tomography. And they got the velocity model of the crash. I don't know if you've seen that. It's a 3-dimensional velocity model.
Yes. So this is the Upi Mishra work that you're talking about, the recent
Somebody from MOES, yeah. So I was wondering,
Mishra.
So how does that compare with what you got here?
Yeah, I think it's quite similar because we didn't have a 3D model, but I think the 3D model looks quite similar. What they don't have is any data from south of the Shillong Plateau, the edge of the Shillong Plateau, because all the MOES stations kind of stop to the north. So they look at the Shillong Plateau and the Brahmaputra Valley, and our models are similar. And that's what we are limited by. We really need to run experiments on either side and collect data across the Daoudi fault. I'm doing that
all data sets should be integrated, and that doesn't happen in India. So.
Yeah. This is one of the major problems, and I've always been a proponent of sharing the data with everyone. Yeah. So, but I have not been successful.
Yeah, great work, Shupio. Very nice.
Thank you so much. Thank you.
I got to drop. Okay.
Yeah.
Another meeting.
I echo the same thing. It was a great talk. Really enjoyed it. Couple of things I want to ask: that has there been any finite element modeling done in this area? I'm sure there must have been, because it's such a complex area. And the second question is that why all the deep earthquakes are to the east, when I look at the all the earthquake plots you have. And is it because of the complexity there with a series of?
Okay. Okay. Yes. Yes. Yeah. So let me answer the first question. So you're talking about finite element modeling in terms of geodynamic modeling of the region?
Right.
Yes. So this is something which we wanted to do. I spoke to someone at GFZ who does this kind of a thing. So when I gave this talk in GFZ, so this person, Sobolev, he was very curious for doing this, because he said that you don't need to do anything other than just loading the plate from either side, and that will pop up the Shillong Plateau. So why don't we model this? But I haven't been successful to work with him so far because COVID came in between. So this was in 2019 when I visited them, and we talked about this. But yes, we haven't. But I would really like someone to do this. One of the people whom I was kind of trying to track was Ajay Kumar, who wanted to do this, but who is now in GFZ at the moment. Maybe we will, but I don't know of anyone else who has done it. But yeah, so I would love to do it. Yes.
Yeah. No, that would be very. I mean, that might support a lot of your work and observations, because I use that actually more on a basin scale back in 95, 96 when I did my thesis. And but I know one of my colleagues actually used it for in a crustal scale, and it was a code by the professor there in Arizona. It's called Tecton. But now 30 years have gone by, so finite element codes have become much more powerful and much more accommodating. So it would be nice to kind of be and this area with so much complexity and all that would really benefit from some of that work. So thank you for I have to drop out, but thank you very much. Really enjoyed the talk.
Yeah, thank you so much. Yeah,
Great
deeper
information.
sorry, you asked about
Yeah.
Yeah, obviously, the Indian plate obviously is subducting underneath the Indo-Burman ranges. So that's what's producing all the deeper earthquakes. So they are all in the Indian plate, but it's kind of going deeper and deeper as you go to the east. I didn't talk about that aspect because of the bar of time. But yes, we see that the Indian plate is kind of flexed down in that direction, and that's what's producing all these deeper ones. Yeah. So you see the smaller beach balls, the deeper ones. That's what I ignored for this talk. Yeah. Those are the ones.
But makes sense. Yeah. Thank you so much.
Thank you.
Yeah. Thanks, Amit and Sanjay. We'll talk to you guys later. Bye.
Thank you. So if Dhananjay is also here. So Dhananjay, thanks for joining. I know you were not available today. So
yeah, I got a meeting at the last moment. I just heard the last 15 minutes. So and also earthquake, I'm forgetting all those details. I'm mostly focusing on the exploration side, but yeah, looks good. Yeah, good to get some earthquake folks showing us their work. Thank you, Supriyo.
Yep, you're welcome.
So we are past the time, means unless people want to hang around and talk, I'll stop recording now. Thank you.
Yeah. Sorry, did I take more time than?
No. It is just we started like 10 minutes late. You were done 10 minutes early, so that's
okay. Yeah.
Fine. And this setting is more